subscribe.
Yeah. Hey y'all, welcome back. Today we're reviewing logarithmic functions. So these first few problems, we're just rewriting the equation in whatever the other form is. So here we've got some logarithmic equations, and we want to rewrite them as exponential equations. So just in general, maybe I'll make a note up here. If you have log of any base, I'll just call that base b, of a power, I'll call that p, equals an exponent. I guess I'll call that, I want to call it e, but e is kind of a reserved letter here. We'll call it x for exponent. That seems good. So if you've got an equation written in this form, we can rewrite it as the base raised to the power of the exponent. Remember that a logarithm is an exponent. So b to the x equals the power. So here base, power, exponent. So both of these statements are equivalent. We can go back and forth, and with 1a here, we're going to rewrite this as 3 to the negative second power equals 1/9. Part B, we've got log, and notice how there's no base written here. Whenever that happens, it's assumed to be 10. It's called the common log. So 10 to the 0th power equals 1. Make sure as you're writing these equations, just kind of double check them with your calculator and make sure they actually make sense. You know, that 10 to the 0 actually is 1. On number 2, we're going the other way. So we're going from these exponential equations to logarithmic equations. So 5 squared equals 25 can be rewritten as log base 5. The base is the base in both cases. The power here is 25, and the exponent is 2. So log base 5 of 25 is 2. Remember that a logarithm is just an exponent. So this logarithm equals the exponent. Letter B, we've got Euler's number E. That's kind of why I didn't want to use E up here. E is generally used as a constant to represent Euler's number. It's about 2.7. It's an irrational number, kind of like pi. Yeah, so we want to rewrite this as a logarithm. This is going to be, whenever you have a base that's E, what you don't want to do is you don't want to write log base E. Well, I thought I could copy-paste that. That didn't work. Don't write it like this. This is kind of like what we're trying to say here, but I am going to change this, so hopefully you're not just copying what I'm writing here. This is basically what we want to say, but it is not conventional to use Euler's number as a base, or let me restate that. It's not conventional to write Euler's number when it is the base. Instead, we write ln, which stands for natural log, although it is backwards here, NL, okay, natural log. Yeah, so here we go. Anytime you see this ln, that means natural log, and that means that the base is Euler's number. So before we go any further, just want to clarify here that we've got two what we call special logarithms. The common log is when you have base 10, and in that case you don't actually write any numbers here. The natural log, instead of writing a number here for Euler's number as the base, you just write ln. I want to make sure that that's very clear here. Okay, moving right along. Number 3, we're evaluating these, and you really don't need a calculator for any of these. I'll bust out the calculator when we need it. There will be a couple problems where we need a calculator, but these are not them. What you want to do is you want to think of 2 to what power is 64? That's really what this question is asking. That is what this logarithm equals. Remember, it equals the exponent. So 2 to what power is 64? Well, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64. So my answer here is just 6. All right, I'm evaluating this expression, so I'm just trying to say what this thing actually equals. Okay, so part B, 5 to what power is 1? 5 to what power is 1? Well, pretty much anything to the 0th power is 1. Almost every real number. There's one little exception there. I don't really want to get into it. It's a whole discussion in and of itself. 0 to the 0th power is undefined, but just about every number that you're actually going to see with these logarithms, because the base can't be 0 anyway. But yeah, anytime you see a 1 inside the parentheses, then it's going to equal 0. Log base 2 of 1/4. Okay, so this one's a little trickier. 2 to what power is 1/4? Now you might notice that 4 is 2 squared. So you could think of this as like being 1 over 2 squared. So in order to get this power in the denominator here, we need a negative exponent. So this is going to equal -2. Part D says the natural log of e to the 11th. Now the base is not explicitly written here, but it is implied to be Euler's number e. So e to what power is e to the 11th power? I think this one becomes a lot more obvious when you write it out like this. So, get in the habit of just thinking about these logarithms as trying to figure out what the exponent is. So if you have e to some power is e to the 11th, then this something would have to be 11. Log base 2 of 32. This is going to be very similar to part A. Okay, 2 to what power is, instead of 64, 32. So that would be 2 to the 5th power. Okay, so there's number 3. I'm evaluating a bunch of logarithms. Number 4, we are just rewriting these logarithms kind of like how we did in number 1, except we're going to use that technique to solve for x. So 4a, I'm going to rewrite this as 4 squared equals x. So x is 4 squared is 16. Part B, the base here is x, so we get x squared equals 144. And then we need to take the square root of both sides to get x, so we get x equals, now algebraically, if we just started here, we would get plus or minus 12. But the base of a logarithm, since this is the inverse of an exponential function, and this goes for exponential functions too, the base cannot be negative, or else it's not exponential. And so since the logarithm is the inverse of an exponential function, this base cannot be negative, so we're going to disregard the -2 as a solution. Think of it as like an extraneous solution. Number 5, here we are just rewriting these expressions using those properties we talked about. So we're just trying to expand these. We're going to try to write this as a sum or difference of multiple logarithms, where each logarithm only has a single factor inside of it. So I'm going to take I'm going to take 2 steps to work this one out. Log base 9 of, now we've got 2 factors being multiplied here, right? Q to the 0.6 and R to the 0.4. So whenever you have a logarithm of a product, you can split those factors up using addition. This is called the product property. Okay, and it's really an offshoot of the product property that we have for exponents. In fact, it's just really a rearrangement of that one. So q to the 0.6 power, and then we got log base 9 of r to the 0.4 power. That would be our first step, is to split those up. And so now we got to deal with these exponents. And we have a power property that allows us to rewrite a logarithm if there is an exponent in our argument here inside the parentheses. We can rewrite it so that that exponent is actually a coefficient of the logarithm itself. We talked in class about why that's true, why that works, but at the end of the day, just remember that it does. Okay, so here we go. So that's about as expanded as we can go. Notice now in each logarithm, they only have a single factor. So when it says expand the logarithms, your final answer should have no exponents. That's kind of what I'm talking about here. Letter B is going to be kind of similar, except we're dividing instead of multiplying. So we're going to use that quotient property. Also log base 9, look at that. So log base 9 of r cubed minus log base 9 of q to the 6th. Right, and then we're going to use the power property, just like we did over here in A. We're going to move these exponents down to be coefficients. So I'm also move this power of 6. There we go. Yeah, that's it. So there's your answer for part B. Okay, well, that wraps up page number 1. Let's move on to page number 2. Number 4 has us condensing the logarithm expression, so we're kind of doing the opposite of what we did in number 5. So we want to condense these. We want to try to write this as a single logarithm. So when you have two logarithms that have the same base here, oops, what's going on here? There's two logarithms with the same base, in this case base 2, you can multiply the two arguments together. So we have 1 over x times 1 over x squared. Whoa. And we can simplify this just a hair further. We can multiply these together. Our final answer here is going to be log base 2 of 1 over x cubed. You can also write this as log base 2 of x to the negative 3rd power. I guess I'll go ahead and write it like that just so you can see an alternative correct answer. You don't have to write it like this, but this would be correct as well. 1 over x cubed is equivalent to x to the negative 3rd. So these two would be equivalently correct answers. Letter B, before we can combine these, we got to take care of the coefficients. So we're going to rewrite these so that the coefficients become exponents of the argument. So natural log of 6 cubed minus the natural log of 3 squared. Okay, well here we've got 6 cubed, which is, let's see, 6 times 6 is 36, times 6 would be 216. So this is going to be the natural log of 216. When we're combining logarithms that are being subtracted, as long as they have the same base, we're going to divide the arguments. So when you add two logarithms with the same base, you can combine them using multiplication. And if you subtract two logarithms with the same base, you can combine them using division. 3 squared is 9 here. And let's see, 216 divided by 9. Let's see, that works out. That would be 24. So what we get here is the natural log of 24. Number 7, now we're getting into solving equations. So when we use the one-to-one property, we use that whenever we have a single logarithm on both sides of the equation. And what we can do here is anytime we've got an equation set up where we've got the same log with the same base on both sides of the equation, we can just set the two arguments or what's inside the parentheses equal to each other and simply solve from there. So I have 5x plus 1 equals 6. I can subtract 1 from both sides to get 5x equals 5. And then finally divide both sides by 5 to get x equals 1. For part B, I can do the same thing. That one-to-one property allows me to drop these logarithms because they have the same base, which is 10. So that gives me 2x minus 7 equals 11. I can add 7 to both sides and get 2x equals, let's see, 11 plus 7 would be 18. And then divide both sides by 2 and get 9. And whenever you solve these logarithmic equations, you do have to check for extraneous solutions. And they will arise anytime you get a solution that if you plug it back into the equation, you get a negative or a zero number inside the parentheses. So you do need to do a domain check, and I probably should have done that before actually boxing either of these answers. But just to check one real quick, if I plug in 1 here, I get 5 times 1 plus 1. That's going to be positive. So this one checks out. And on part B, if I plug in 9, I get 2 times 9, and that would be 18 minus 7. That's also positive. So we don't have any issues, any domain problems with any of these two solutions. They both check out. For number 8, A, first use the product property to combine the two logarithms. Then use the inverse property to rewrite the logarithmic equation as an exponential one. Distribute the 5 and cube the 2 to get 5x plus 5 equals 8. Subtract 5 from both sides to get 5x equals 3. Finally, divide both sides by 5 to get our solution, x equals 3/5. For B, first use the product property to combine the two logarithms. Then, use the inverse property to rewrite the logarithmic equation as an exponential one. Distribute the 3 and square the 6 to get 3x plus 15 equals 36. Subtract 15 from both sides to get 3x equals 21. Finally, divide both sides by 3 to get our solution, x equals 7. Number 9, we're going to use the quotient property to solve these. So I'm going to rewrite this one as the natural logarithm of 5x squared. And since we're subtracting these commonly based logarithms, we can combine them using division. Equals 3. Now since x can't be 0, otherwise this would be 0 and the whole equation would be no good, we are going to be safe to actually divide this out, right? So this is going to reduce. 5 over 5 is 1, and x squared over x is just x. So that's going to be natural log of x equals 3. Now we can rewrite it using an exponential equation. E to the third power equals x. E is the base of this natural logarithm, and that's where that's coming from. Part B, same idea here. We're going to set this up using a single logarithm, log base 3, and we can combine the two logarithms using division. And before I go any further, I am going to simplify that expression inside the parentheses. 4x divided by 2 would be 2x. 10 divided by 2 is 5, so this would be 2x plus 5. And now that I've got my logarithm isolated, I can rewrite this as an exponential. 2x plus 5 equals 3 to the 4th. 3 to the 4th is going to be, let's see, 3 times 3 would be 9. And times 9 would be 27. Times 3 would be 81. So we've got 2x plus 5 equals 81. We can subtract 5 from both sides. So we get 2x equals, would that be 76? Yeah, I think so. And then 76 divided by 2 would be 38. So x is 38. All right, and I neglect to do my domain checks here, but everything looks to be positive on both of these questions. So I'm going to go ahead and say, yep, both of these are good solutions. Number 10, some more solving. All right. So part A, I almost have two logarithms on both sides, so I can use that property, but what I need to do is move this 2 so that it's an exponent. So I got log of 7x minus 12 equals log of x squared. And now that I've got just a single log with no coefficients or anything like that, I can go ahead and drop the logs and just set what's inside the parentheses equal to each other. 7x minus 12 equals x squared. I do have a quadratic here, so I want to rearrange this so that it's equal to 0. X squared minus 7x plus 12 is going to equal 0. And I can do that, get that, by subtracting 7x on both sides and adding 12 to both sides. Yeah, this looks like it is going to be factorable. So two numbers that multiply to give me 12 and add up to negative 7 are going to be negative 3 and negative 4. And so setting each one of these equal to 0 and solving them individually, I'm going to get x equals 3 and x equals 4 as potential solutions. So let's take a look at our domain here and make sure we don't have any issues. If I plug in 3, I get 3 times 7 is 21, minus 12, that would be positive. 3 is obviously positive, so 3 is going to be a good solution. And if I plug in 4 times 7 is 28 minus 12, that's positive and positive. So I think this might be our first one where we actually get legit two solutions, and they both check out. Letter B. Really want to try to use the one-to-one property here, but this 3 is kind of in the way, unfortunately. So what I'm going to do is I'm going to subtract that log base 2 that's currently on the right-hand side of the equation and move it over to the left, and we can combine, we're going to end up combining these two logarithms, using the quotient property. So I subtracted the log base 2 of y minus 6 on both sides. And so now I can combine these two logarithms. Notice they're being subtracted, so I can combine them using division. We get log base 2 of y plus 1 over y minus 6 equals 3. I've got a logarithm isolated here, just a single log, so I can now rewrite this as an exponential equation. Y plus 1 over y minus 6 is going to equal 2 to the power 3. 2 to the power 3 is just 8, by the way. So I'm going to kind of do two steps in one here. 2 to the power 3 is 8. And then I'm going to multiply y minus 6 on both sides. So that's going to give me y plus 1 equals 8 times y minus 6. A little afraid I'm going to run out of room here, so I'm going to scoot all this up just a hair. Just enough to give me some room to work here. Okay, so I need to distribute that 8. I get y plus 1 equals 8y minus 48. And now I just need to kind of move around my y's and all my terms, and I should be good here. So if I subtract y from both sides, that's going to leave me with a 7y. And then if I add 48 to both sides to get rid of this one, 48 plus 1 is going to be 49. And if I divide both sides by 7, I do get y equals 7. Before I box it, I'm going to do my domain check here. 7 plus 1 is positive, 7 minus 6 is positive. So we are good to go. This is going to be our solution. Letter C is, I guess it looks like the easiest one of all three of these, because this is already set up, ready to go, so that I can rewrite it as an exponential. 3x plus 1 equals 10 squared. Remember that the base of the common logarithm is 10. So if you don't see a number here, it's assumed to be 10. So 3x plus 1 equals 100. Subtracting 1 from either side is going to result in 3x equals 99. When I divide both sides by 3, I get x equals 33. A quick domain check here, 3 times 33, that's going to be positive, so this checks out. Okay. Let's take a look at number 11 here. It says the population of Pi Town was 23,450 in 1998. Its population decreases at a rate of 3.12% per year. Write a function rule to model the scenario, and then find what year the population reached 12,440. So this is going to be an exponential decay equation, and our general format for that equation is going to look something like this. So the initial population in 1998 was 23,450. The rate of decrease was 3.12%, so that'd be minus 0.0312. And so here's our function rule. Okay, that's the function rule. And so now we want to see what year the population reached 12,440. So we're going to substitute 12,440 in for y here and solve for x. So yeah, I'm just making a little note here that this is our function rule. In other words, what's the equation? Okay, so first things first, I'm going to divide both sides by 23,450. I'm not going to bother trying to simplify it or anything because it's going to be a calculator problem. It's about time we broke out those calculators. I am going to use a calculator here to do this 1 minus 0.0312 just to make sure that I'm, you might be able to get away with doing it without a calculator, but I don't want to leave that to chance. There's no reason to do that. So let's pull this up. Here we go. So we got 1 minus 0.0312. Okay, so that's going to be the new number inside my parentheses here. .9688. All right, so now we got a nice little equation here. We're going to rearrange this for x. So x is going to equal log, and then the base is going to be that 0.9688 of this fraction. Okay. So, assuming you do not have one of the newer calculators, we are going to have to put this, we're going to have to use the change of base formula to actually type this in the calculator if you've got a scientific or one of the older TI models. So I'm going to rewrite this, as x equals, we're going to change it to base 10, although technically you could change it to any base you want. I'm going to go base 10 here. Log of that fraction divided by log of the base, the 0.9688. And so this is what we're going to type in the calculator here. So we got log of this big fraction here. Divided by the log of 0.9688. Okay, so basically 20, almost exactly. So what I'm going to do is I'm going to say approximately, I mean it's almost exact, but approximately 20 is what my x value is. So what year did the population reach 12,440? Well, 20 years since 1998. So that's going to be in the year, what would that be? 2018 would be the year? Yeah. Okay, very good. Okay, so that takes care of page 3. Let's move on to page 4. Number 12 says in 1998 there were 3,116 computer security incidents. The number of incidents increased by 80% per year. Geez, you can get some new IT people. In what year were there 42,031,169 computer security incidents? Okay, so we need to first write an equation to model the scenario. So y equals, we'll use 1998 as our initial amount here, 3,116, times, we are seeing exponential growth here, 1 plus 0.8 to the power of x. So this is just going to be our model here. And so we want to know in what year, so we're going to be solving for x here. We're there 42,031,169 computer security incidents. So that's going to be our y value. We're going to solve for x. So the first thing we need to do, and I guess I'll kind of do two steps in one here. I want to combine this 1 plus 0.8 to make it 1.8. And then I'm going to divide both sides by 3,116. So let's go ahead and do that. We'll divide both sides by that 3,116. What is going on here? There we go. Sorry for the technical difficulties there. So yeah, we're going to divide so that this thing goes away on the right-hand side, and 1 plus 0.8 is going to be 1.8. And so now we're ready to rewrite this as an logarithmic equation. So x is going to equal log with a base of 1.8 of this big old fraction here. And so this is something we'll type into the calculator. Let's go ahead and pull that up. Okay, so we've got, so we need to rewrite this using the change of base formula. So we're going to have log of this big fraction divided by log of 1.8. So that's going to be what we type in here. So we can make a big fraction here, a log of, make sure I type this in right, 42,031,169 over 3,116. Pretty big number there. Over the log of 1.8. All right, so let's see what we got here. About 16.178, so we'll say x is not pi, is approximately 16.178, and I guess I would round up to 1. So it says in what year? So what we need to do is, this is the number of years since 1998. So to get our answer, we're going to do 1998 plus that 16.179, and really, you know, the 0.179 just means we're about almost 2/10 into the year. What would that be, like February, March, something like that? So we don't really need to add an extra year here. We just need to add the 16. And so we're going to get in the year, so let's go ahead and answer our question here. Can't really see. Let's hide this calculator so you can see what I'm doing. Okay, so yeah, 1998 plus 16 is going to be 2014. And so to answer our question, we're going to say in 2014, there were 42,031,169 computer security incidents. Okay. Number 13 says the value of a truck decreases 18% each year. So we're going to have an exponential decay situation here. The current value of the truck is 52,000. All right, my rate is going to be 18%. Here's my model, and we want to know after how many years will the truck be worth $20,000. So $20,000 is going to be our final amount here. And we're going to go ahead and solve this equation for x. So just like with the last problem, I'm going to do these two steps in one. I'm going to divide both sides by, 52,000. And usually at this point, I'm not a big fan of reducing, but since all of these are, in thousands, I think we can go ahead and safely, we don't necessarily need to reduce the whole thing, but if we just divide both sides by both of these by 1,000, we can reduce this to 20 over 52. So I'm going to go ahead and do that. And then 1 minus 0.18, that'd be like 100%, minus 18% would be 82%, so 0.82. And now we can rewrite this as a logarithm. We've got this exponential equation. We can say x is equal to log base 0.82, or 82%, of 20 over 52. And let's see, that's going to equal approximately, and this is going to be where we get the calculator out, so let me bring that back up. All right, so we got log of, not this huge number like in the last problem, but just 20 over 52. Okay, over log of 0.82. You know what, I just realized I didn't actually write this in using the change of base formula, so I'll go back and do that. Oop, not 0.28, but 0.82. And we get about 4.814. So first of all, let's rewrite this using change of base formula. We got log of 20 over 52 divided by the log of 0.82. So x is going to equal, x is going to equal approximately 4.815. And that's how many years. So we'll say, if we're going to answer this question in context here, I'm going to say the truck, or the truck's value, will be $20,000 in approximately 4.18 or 815 years. Okay, there's your answer for number 13. We've got one last problem here, and then we're done with the review. Number 14 says Americium? I don't know how to pronounce that. 241 has a half-life of 432.2 years. In 2023, you have a 100-gram sample of the radioisotope. In what year has the sample decayed to only 10 grams? So our equation for half-life is going to be y equals the initial amount, so that would be, 100 grams, times 1/2 to the power of the number of years, which is what we're trying to solve for, call that t, over the half-life, which is 432.2 years. We want to know when, in what year does this decay to only 10 grams, so we're going to solve for t, we're going to set y equal to 10. So we're going to divide both sides by 100. 10 over 100, which would be 1/10, okay, 0.1, if you will, equals 1/2 to the power of t over 432.2. And so now we can rewrite this as a logarithm. So t over 432.2 is going to equal log base 1/2 of 1/10. Before I use change of base formula, I want to multiply both sides by this 432 so that I can get t by itself. So my exact answer here would be 432.2 times log base 1/2 of 1/10. So yeah, we want to put this in the calculator. We will use the change of base formula to write this in a way where we can actually type it in the calculator if you have one of those older calculators. So we have t equals 432.2 times log of 1/10, 0.1, oh, nope, not the whole thing over, just the logarithm, over log of 1/2. Okay, and whatever that is, that'll be our t value, and we can add that to 2023 to get our year. So let's go ahead and type that in. 432.2 times this fraction, which is going to be log of 1/10 over the log of 1/2. All right, we get, oh geez, wow, okay. 1,435.737. Okay, so we need to add this number to 2023 to get the year. So you have 2023 plus the 1,435. And just to be safe here, I'm gonna type that in too. 2023. We can sort of disregard the decimal here, because whether it's like 0.1 or 0.2, we're still in that year. You know, January and December are both in the same year, regardless if it's like 1/12 or 11/12 into the year. So in the year 3,458. Okay, so to answer our question here, just move this up so you can see everything. Let's go ahead and type out our answer. So the sample will decay to 10 grams in the year 34, it doesn't even sound like a year, 3458. So yeah, we're gonna have to find someone else to verify that by the time the year rolls around. Okay, there you go. There's number 14, and that will conclude today's review. I hope you enjoyed the video. Y'all have a great day, and I'll see you next time.